So we just finished taking a look at Aristotelian logic or categorical logic, where our main focus and interest was understanding the logic that occurs between assertions of how categories relate with one another. So, for instance, take the category of cat, take the category of mammal, and you think of a proposition, all cats are mammals, and that tells us that it makes the assertion that those categories relate such a way that the category of cats falls completely within the category of mammals. And then given what other kinds of propositions are conjoined with that categorical proposition, there's going to be certain implications. And studying that allowed us to be able to determine whether categorical syllogisms are valid arguments or invalid arguments. The problem with that is the logic of Aristotelian logic and categorical logic is limited then to categorical syllogisms. But there's all sorts of other arguments out there, and so we need to learn another type of logic to be able to understand how those relate and what the implications are given certain propositions. And that's going to take us to propositional logic. So let me explain a little bit the difference between categorical logic and propositional logic, and then we'll start developing it as a system. So I'll have you become familiar with some of the symbols that we use to symbolize statements in propositional logic. So in categorical logic, as I was just mentioning, we might have the category of cats and the category of mammals. And then we make an assertion about these categories. For instance, all cats are mammals. Well, since we were interested in those categories, what we would do then is represent such a statement as something like all C are M, where C represents our subject term and M represents our predicate term. And we do that because in categorical logic, our focus is how these categories relate. So of course, as our subject terms and our predicate terms become more complex, it's very helpful to leave the form, so leave the form words, and then strip away the content, cats and mammals, by just leaving them as these capital letters C and M. And that's a very helpful way to investigate and see the logic that's occurring between these. In propositional logic, instead of predicates in subject terms, what we become interested in are whole propositions. So for instance, let's take a couple of simple propositions. You might have it rains, and the grass is green. So notice that each of these propositions is simple. It's a simple proposition because it's one clause that makes a well-formed statement. And as such, instead of representing categories such as rains or grass or green, we represent the whole proposition using capital letters. So we can let R stand for it rains, and we can let G stand for the grass is green. And then notice that we can relate those propositions in all sorts of different ways. I might say, for instance, it rains and the grass is green. I might say it rains or the grass is green. I might say if it rains, then the grass is green. I might say it's not the case that it rains. I might say it's not the case that it rains and the grass is green. All sorts of things, right? So I might even say it rains if and only if the grass is green. And what propositional logic is going to allow us to do is unpack the logic that's underneath, surrounding, or hidden, contained in those different connectives, those different ways of relating these propositions together. So as one example, if we say if the grass is green, then we're going to be in a position to say if R then G. And we'll talk about this symbol in a moment, but it represents material conditional, the if then. And now instead of having a simple sentence, this is a compound statement. And then if we add other types of statements in an argument, so we could take this as our first premise, and we might have another premise, it is not the case, for instance, that the grass is green. And not the case sign is going to be a tilde, as we will see. And then propositional logic has a set of rules that are truth-preserving rules, so the rules about valid inferences. And as we come to understand those rules, then we will be in a position to show that if premise 1 is true and premise 2 is true, it can't be the case that R is true. It can't be the case that it rains. So we will be in a position to say not the case R. So that gives you a sense of where propositional logic is going to head, a very simple sense of where propositional logic is going to head. But what I want you to take note of at the moment is that what we can do with these propositions is we can represent them completely with capital letters instead of categories. So that's the case for it is rains, or it rains. That's the case where the grass is green, or any other proposition. So any given proposition, whether a simple proposition or a compound proposition, they can be related, logically speaking, to any other proposition in all sorts of different various ways. And in contrast to categorical propositions and categorical logic, where what we would do in representing those statements clear to ourselves, we would take out the content and leave what we called the form words. So again, if we think about all cats are mammals, what we would do is we would take out the content by representing our subject term and our predicate term with capital letters, and we would leave the form words all and are. Instead, now with propositional logic, we have our whole statements. So for instance, go back to R and G, it rains and the grass is green. We have whole statements. And what we're interested in is how these, for instance, in this case, simple statements, R and G, how they might relate logically speaking. In order to represent the various types of relations, instead of leaving the words, we introduce logical connectives. So let's talk about the various logical connectives that are standardly given in propositional logic. So we have logical connectives for the following logical relationships: negation, conjunction, disjunction, material conditional, and biconditional. So for negation, we use the symbol tilde. It roughly stands for not, or it is not the case that. For conjunction, we use the symbol dot. You might think of it as roughly standing for the word and. We have disjunction, and we use the wedge, looks like a lowercase v, and that roughly corresponds to or. For the material conditional, we have the horseshoe, and that roughly corresponds to if, then. And for the biconditional, we have the 3 bars, which roughly stands for if and only if. For the negation symbol, for any proposition P that we might have, so let a lowercase p be a variable that can take any of our capital letters, so it can take any proposition. So for any proposition, we attach it to the front. So this is a unary connective because it only connects up to one proposition. Now that proposition could be compound, as it were, or it could be simple, but it goes out to the front. For conjunction, it's a binary connective, and it goes in between our propositions. So this is lowercase p, lowercase q, supposed to be a lowercase q, and q also is a variable that will take any proposition. For our disjunction or our wedge, it's also binary. For the rest of these, they're binary, and they occur between propositions. So for our if-then, we put the horseshoe in between the p and q, and same for the material equivalence, or for the biconditional, it goes in between them. So what that means is that we have to order our symbols in a particular way, or we're going to end up with something that's just gibberish. So take negation as an example. We have P and then try connecting the negation afterward. It won't be meaningful because the negation needs to connect to the front of a proposition, to the proposition that is modifying. Or if you try to just have, for instance, P dot, whether it's this way or whether you put it before the P, those will not be well-formed formulas because the dot, like all the other connectives besides the negation, are binary connectives. It's a binary connective. And that means it needs to be connecting to some other proposition in order for it to be meaningful. So that's going to be true for all the other binary connectives. But then we can even introduce parentheses, which adds a new wrinkle to things. So if we have a proposition, for instance, P and Q, and I put it in parentheses, the parentheses tell me to treat this as an entire unit, which means I can take connectives and modify or put it in all sorts of other kinds of logical relationships. So maybe, for instance, I want to connect a tilde. So now I'm not just negating P, and I'm not just negating Q. What I'm negating is P and Q. I'm saying that's not true. It's not the case, both P and Q. Which is different, and you might not think it's different, but that's different than saying it's not the case P and it's not the case Q. Now, both of these statements are well-formed formulas. And we can make things even crazier, if you will, because I could put parentheses around this statement and then put a horseshoe between here. And now what I'm saying is, if it's true, if this is true, then this is true. So if it's true that it's not the case, both P and Q, then both it's not the case P and it's not the case Q. This symbol in this very complex or very compound proposition that we have here, the horseshoe is what we call the main operator. And it tells you that most fundamentally, this statement is a conditional statement. Because most fundamentally, it's comparing, or it's relating this complex statement, the one on the left, the antecedent, and this statement, the one on the right, which is our consequent. And there's different ways in which you can pick out the main operator, be able to find it. One way that I've been trying to suggest is that you can, with these parentheses, you can get in your mind that they're being treated, to treat those as units, as almost as if they were simple propositions themselves. And then you want to see what the symbol is that's not within any of those parentheses, that's relating the compound sentences that are within those parentheses, and that'll tell you what the main operator is. The other way is to work mechanically from inside the parentheses to outside the parentheses, and your main operator is going to be the one that's not embedded in those parentheses, the least embedded one. So for instance, let me draw up this again. The page has gotten convoluted. All right, so suppose, again, we have not the case P and Q. And we're saying if that's true, then it's going to be true. It's not the case both P and Q. I'm sorry, it's not the case P and it's not the case Q. And notice that this logical connective is within a parenthesis. This is within a parenthesis. They're unary, so we need to treat them, whatever they're connecting, as units. And then they're being conjoined by a conjunction symbol, the dot. But that's within parentheses, so that can't be our main operator. This is within parentheses, so that can't be our main operator. Now this isn't within parentheses, but it's a unary connector, And so we need to treat it and the proposition that it is connected to, in this case, the compound sentence P and Q. And we treat that as a unit. This then is going to end up being our main operator. It's not embedded in our parentheses, and it is connecting two statements independently. You can have a negation as a main operator. So very easily, I can show that by modifying this sentence by adding another set of parentheses and adding a negation to it. Before, I was saying that this is true, that's what we would be asserting. Now what I'm saying is that's false, this is false. So let's take a look at these logical connectives in more detail and get a better appreciation of just what they mean. So first, let's talk about what negation means roughly, or what it roughly corresponds to in English. So the negation symbol roughly corresponds to saying not, or it is not the case that. So if we took, for instance, our statement R rains, and we negate it with our tilde, we're saying something like it isn't raining, or it is not the case that it rains. Now, to understand the negation better, we can use what's called truth tables, and I'll have a chance to illuminate these more for you and discuss them in more detail on how to construct them. But they'll still help us understand the meaning of negation. So with the truth table, we'll take P as our variable, and we're interested in what this statement, it is not the case P, means. And of course, our variable can take both simple statements, simple propositions, and compound propositions. Well, if we're just thinking about P, there's two cases for any particular statement. It could be true, or it could be false. So our first line here represents the case, or the circumstances in which P turns out to be true, where our second line represents the case in which P turns out to be false. So for instance, there's a set of circumstances in which it's true that it rains, but there's also a case in which it's false that it rains. So if we think about those cases, and we stay, or we assert, that it's not the case P, what we're saying, or what we're asserting, is, in short, is it's false P. So in line 1, where P is true, and I'm saying that it's false, I'm wrong. And since I'm wrong, it gets the value false. But in the second case, in which P is false, and I assert that that's false, that it's not the case P, then what I'm saying is correct. It's true. So then, re-examining this, what we see is that our symbol tilde tells us that any time what it's connected to is true, then what it is saying is false. And anytime what it's connected to is false, then what you're asserting is true. So it tells us to flip those values. And that's its logical meaning. Conjunction, or the dot, roughly corresponds to and, but, yet, moreover, however, furthermore, etc. Anything where in English, normally when we use those words, it commits us to the clauses that it connects to both be true. That's the important part of conjunction. When I say, for instance, that the grass is green and it's raining outside, I'm committing myself to both of those being true. So if it ended up being that the grass is green, but it's not the case that it's raining outside, it's sunny outside, for instance, you would say that what I've said is false. You'd say, well, you're wrong. That's incorrect. So let's flesh this out a little bit more using truth tables. So we might have it's raining and the grass is green. So just for illustration, we might let R be taken under the variable P, and we might take G to be taken under the variable Q. But keep in mind that this is going to hold for any conjunction, since these are variables and can take any statement. So since a conjunction is a binary connective, we have to be worried about two propositions, P and Q. And what we're asserting is P and Q. Turns out that unlike the negation, where we only had two circumstances to worry about, we're going to have to worry about four circumstances. And that's because there'll be a case in which the Q is true, and then a case in which it's false. But maybe the P ends up being true in both these cases. But not only that, not only can the P be true, right? But there's a case in which it could be false. Well, maybe then we can have the situation in which P is false and Q is true, and the case in which P is false and Q is false. And we need to account for each of those possible circumstances in order to get the full meaning, in order to express the full meaning of P and Q. So then imagine when somebody comes up off the street to you and says, it's raining and the grass is green. When would you allow that to be true, and when would you say that's false? Well, if you looked outside and you saw that it was indeed raining and the grass is green, you would say that's true. But if somebody says, it's raining and the grass is green, and then you look outside and you see that it's raining but the grass is brown, you'd say that's false. In that situation, in our second situation, you say that's false. Or if you find out that it's not raining but the grass is green, so it's a sunny day but the grass is green, you'd also say that's false. Or if it's sunny and the grass is brown, you would say that's false. The only situation for conjunctions when you're going to say that it's true is when both of the statements being connected by conjunction, which we call conjuncts, it's only when both of your conjuncts are true. So this expresses the logical meaning of conjunction. It's true when both of our conjuncts are true. It's false in any other circumstance. So now let's take a look at disjunction, the logical relation disjunction, which roughly corresponds to the English or, either or unless. And it's important to remember that we're interested in the inclusive disjunction. So if I say either this statement is true or this statement is true, for us, we allow that compound statement to be true when one option is true, the other option is true, or even the case in which both of the options are true. And we can represent that very easily with our truth tables. So again, since this is binary connective, where you have to be worried about two statements, and we use the wedge to represent disjunctions, so that says either P or Q. So either it rains or the grass is green. So we have a situation in which the grass can be green, and a case in which maybe it's not green. We have the case in which the grass is, where it does rain. But we also have the situation in which it doesn't rain, but the grass is green in one case and then false in the other case. And that exhausts all the possible circumstances. So we said the inclusive disjunction is true when either one of the disjuncts is true or when they're both true. They're both true in our first circumstance, so it gets true. Now it rains, but the grass isn't green, so we say it's true. Now it doesn't rain, but the grass is green, so we say it's true. The only time we say that it's false is when neither of the options that we say is true. So if I say either it rains or the grass is green, and then you look outside and it's sunny and the grass is brown, you'll say, well, that's false. In any of the other cases, we're going to say it's true. Our next logical connective that we want to take a look at is the material conditional. And roughly speaking, the material conditional corresponds to if-then statements in English. So for instance, if it rains, then the grass is green. If it rains, the grass is green. The grass is green if it rains. It rains only if the grass is green. So those are different manifestations of the material conditional, or roughly speaking, in English. Now, in the case of material conditional, it doesn't fit the English ways in which we use if and then as intuitively as, say, for instance, conjunction corresponds with the word and in English. So this is a kind of difficulty. The way to think of material conditionals is that it's giving you a law, it's making you a promise. So if the antecedent, then the consequent. I promise you, you get the antecedent, you're going to get the consequent. That's the promise that you're making. So notice that if your antecedent ends up being false, you can't break your promise. It's impossible to break the rule in the case in which the antecedent condition doesn't occur. So let me flesh this out for you with a truth table. So again, we're connecting two statements. It's a binary connective. So we have to worry about 4 situations. And these are each of my situations. So for helping us think about it, we can let P be it rains, we can let Q be the grass is green, and we're worried about the statement if P, then Q, if it rains, then the grass is green. So what I'm saying is I promise you in the cases, so this is the way to think about it. I'm promising to you that in the situation in which it rains, you're gonna find out that the grass is green. And then you can ask yourself, well, when do I break my promise? Do I break the promise in the case in which it rains and the grass is green? No, I don't break my promise there. Do I break my promise when I say, when I assert if it rains, the grass is green, and then you find out it does rain, but the grass isn't green? That's the case in which I break my promise. I promised you that when it rains outside, you look outside, you're going to see green grass. But here, you look outside and you see that it's raining, but the grass is brown. I broke my promise to you. But now, if I promise to you that whenever it rains outside, the grass is going to be green, and it's not raining outside, I haven't broken my promise. So it's true. And for the same reason, in circumstance 4, it's true. No matter what the consequent is in that case. Now that strikes people as counterintuitive, but that is what the material conditional means. So even if that's counterintuitive, you just have to understand that that's what it means for our purposes. The last logical connective that we're going to take a look at is the biconditional. And what the biconditional says is that you get one with the other. So, for instance, blank just in case blank. It rains just in case the grass is green. Or it rains if and only if the grass is green. And that's what we say in the English. And basically what's happening with the biconditional is that it's a conjunction of two material conditionals running in the opposite directions. So it's equivalent to saying both, if the grass is green, then it rains outside, and if it rains outside, then the grass is green. So it's asserting both of those at the same time. Okay, so we can again use our truth tables to express this. So this is a binary connective like our other ones. So we'll be worried about 2 statements and 4 situations, 4 circumstances. And the statement that we're worried about is P if and only if Q. So if I tell you that it rains just in case the grass is green, it'll be true when you find out that it is raining and the grass is green. But if you find out that it's raining and the grass isn't green, but I told you it rains just in that case, it's going to be false. Now, likewise, if you find out that that it didn't rain when the grass was green, and I tell you that's just the case in which it's going to, you're going to say, well, that's false. But our last circumstance, if we think about the biconditional as giving us a rule in the same way that the material conditional does, the last circumstance doesn't break our promise, doesn't break what we're saying. So it ends up being true. So in short, the biconditional compound statement is true just in case the statements that it's connecting, the propositions that it's connecting, share the same truth value, whether they're both true or whether they're both false in either of those cases.